Hello all of you. Welcome to the 27th lecture of the course on analysis and modeling in chemical engineering. In this week, we started talking about heat equation. In the last class, we derived the mass and energy balance on a differential control volume that gave me the equation of heat transfer, that is the heat equation for the conduction case. And then we showed analogy of that with whatever we have in the mass transfer, that is the diffusion equation, and also in the momentum transfer, right. What I want to do now is to apply the heat equation for a simplified case where we can write it in one dimensional form, and then we can see how we can solve it analytically, right. So in this week we will discuss about analytical solutions and getting the equations in the final form where we can solve it. Later on in the next week, we will discuss how we can numerically solve these equations, right. So as you can imagine that in the one dimensional form, we can still have a hope of solving it analytically. As we go to 2 dimensions or 3 dimensions, or even for 1 dimensions when the boundary conditions are difficult, in that case, we have to resort to numerical solutions, right. So in this particular lecture and some of the examples we'll take in the coming lectures, we'll take some cases where the analytical solutions are still possible for a very simplified geometry. So I'm going to basically start with this system. So you have a large slab, think of it like a table, right? At the top of a table, a large slab that is having much bigger length and width compared to the thickness. The thickness is the smallest of the other two, and the length and width is much higher than the other two. And let's imagine that this large slab is either very hot compared to the ambient to begin with, or very cold compared to the ambient to begin with. In both the cases, solutions are the same, but just to make our life easy, let's imagine that it is hot to begin with and the surrounding is cold, but the nothing will change for the opposite, only the value of variables will change. The equations will be the same if I have a very cold slab with an hotter surrounding. So we have basically got the heat equation, general 3-dimensional heat equation, and I will simplify that for this case. And we assume that we have some temperature, some uniform temperature in the slab, that is some T naught, which is for hotter slab much bigger than the ambient temperature TA. And we are imagining that the slab is having the same kind of ambient in all the directions. So we have the same ambient temperature TA above and same below and same along the sides, right. So if, for example, this is not really having the same atmosphere in all the directions, then it is different. Let us say, for example, the slab is kept on a surface that is providing or taking away heat, then the story is different, and we'll do those cases. But in this case, we're imagining the slab, for simplicity's sake, is in an environment where the temperature of the ambient is same all across, and the heat transfer is pretty much same all across the slab from top, bottom, and the sides. Now, if you look at the temperature gradients in the x, y, and z directions, that I have slightly different kind of coordinate system that I am showing here. So x and y is along the length and width, and z is along the thickness, right. So if this is my coordinate system, then I can have the heat equation like this, and if you recall, the Laplacian operator gives me that del square T is dou 2 T by dou x square plus dou 2 T by dou y square plus dou 2 T by dou z square. So we have derivatives of x, derivatives of y, derivatives of z. But now you think about how the derivatives in the x direction compare with that in the y and z direction, right. So let us say I want to get some kind of an order of magnitude estimate of the derivative in the x direction. What is it going to be? So my dou t by dou x can scale something like the temperature variation in the x direction, right. And let us say I begin with the worst possible case, that is in the beginning when the temperature gradient is the highest. Over time, you can imagine that the slab will cool down right? Because ambient is colder and ambient is much bigger than the slab, right? But to begin with, when the gradient is maximum, even in that case, let us see how much this gradient can be. So, the maximum it can be is something like my T naught minus T A, the temperature difference that we have, divided by the length in the x direction, right, or the length of the slab. The dou T by dou y is similarly something like T naught minus T A by the width in the y direction, and my dou T by dou z is going to be something like T naught minus T A by the thickness, let me call it h, in the z direction. Now, clearly h is much less than length and the width. The thickness is very small. As a result, this quantity is much bigger than dou T by dou x and dou T by dou y, right. So, this is much bigger than dou T by dou x, dou T by dou y, and as a result, I can apply the same kind of an argument on the second derivative, just a scaling order of magnitude argument, and by doing that I can drop these terms. What this means here is that if, for example, you have a geometry that is doing some kind of heat transfer and one of the dimensions is much less than the other dimensions, then the gradient of temperature is the maximum in the dimension where the thickness or the length is smallest, because that is where the gradient is going to be maximum, right. So, let us say, for example, if we take a wall in the room and we talk about the ambient temperature and the temperature inside the room, the heat transfer in principle is happening perpendicular to the wall and parallel to the wall, right. But parallel to the wall, you have a much bigger length than compared to the thickness of the wall. So, the heat transfer in the direction normal to the wall is going to be more important, because that is where the temperature gradients are going to be maximum. The same we can extend for a variety of examples to convince ourselves, but the point being that we have only the z direction that is most important in this problem, provided that this condition is being met, that the height is much less than length and width. This is now called a one-dimensional approximation. You can imagine that solving in variables x, y, z is clearly going to be more time consuming or difficult than compared to solving only in the variable x, right. In this case, by the way, I can say x, only the z term is important here. Okay. So, now let me now look at this slab, and now we need some boundary conditions in order to solve this partial differential equation that is already simplified, because now we only care about the z direction. Of course, time derivative on the left hand side and the z direction, the second derivative that has appeared on the right hand side, right. And now we need conditions to solve this equation. How many conditions we need? We need two conditions for z, because we have a second order in time in temperature in z direction. So, we need two conditions which are my boundary conditions, and we need one initial condition for the temperature in time, because we have first order in time, right. So, the order of derivative defines the number of conditions we need. So, in this case, we need one initial condition in time and two boundary conditions in z, right, and we have to see how we can formulate that. But before I even do that, we are going to make an argument here that is purely coming from the symmetry in the system, that since the surrounding of the slab is same from the top and bottom, so therefore, I can actually define a center line of the slab. I can cut a plane from the middle, right. I can cut a plane from the middle somewhere like this in this drawing, and that will correspond to some middle z is equal to 0. And now I can say that we have a half thickness L is equal to h by 2 above it, and half thickness minus L equal to minus h by 2 below it. And what I am saying is the temperature at any value of z now, if I define the coordinate system from the middle of the slab, that is my center line, so z equal to 0 here. So if I go to T plus z, that temperature we get is equal to T minus z. Why is that? Because this point is as far from the ambient as this point, right? And since the surrounding is same in all directions, so therefore whatever cooling action we have, if we start with a hot slab, it must be the same for this point and this point, simply because it is as far from the ambient. The top and bottom doesn't matter, because they are having the same ambient condition at top and bottom, right? So therefore we can make an argument of symmetry, and we can say that the Tz is equal to T of minus z, provided that z equal to 0 defines the central line. And if I kind of move it here, here, and until come to the middle, what you can imagine that if I plot, let us say, temperature versus my z, then the argument which I have given you is Tz is equal to T minus z. It tells me that T has to be an even function, and more importantly, it is going to have kind of a minima at 0. Why is that? Because this is equal to this, this is equal to this, this is equal to this, and eventually the gradient must be vanishing at T0. If the gradient does not vanish, what does this mean? What this means is then my T at some delta z is not equal to T of minus delta z, right? Which is not true, right? Because if these two are equal, the gradient at z equal to 0, that is going to be, I can write something like T delta z minus T of minus delta z by 2 delta z by some kind of an approximation, and that must be vanishing, right? So for an even function, we should have the vanishing of the gradient at the center line. That's what we are assuming as the first boundary condition, right? So dou t by dou z is equal to 0 at z equal to 0. And I don't care about what is happening in minus z direction, because if I can solve for positive z direction, I already have a solution for minus z. I did not worry about this part of the solution. If I know this part, I can get that part simply by using this relation. So I will keep my solution domain only in the positive z direction. Whatever I have shaded in here, this becomes my solution domain, right? And do not worry about the negative direction. That simplifies my computation, and I have now a boundary condition not at the bottom boundary, but at the center line, that the gradient of temperature vanishes at the center line. Okay. The next boundary condition, naturally, now I am looking at now only the half thickness, that is L equal to h by 2, because that is what is my concern. I already have figured out the boundary condition here, that is dou t by dou z is equal to 0. And now I am interested in the boundary condition at the top surface, let us say, right? And the condition here can be figured out by this, right? So whatever is the heat flux that is coming from within the slab to outside, that is what is equal to the outward flux going out of the slab, right? But the mechanism of heat transfer is very different inside the slab and outside the slab, right? So whatever conductive flux, because the slab is a solid, so we will have some conduction happening here. Whatever conductive flux we get from the bottom at the surface, top surface, should be equal to the convection that is going out of the surface, because outside is air, so we have convection there. So at the surface, these heat fluxes should be equal, because that is the energy coming in, and that energy should be kind of going out. There is no accumulation there really, because there is no volume in the surface, right? The surface volume is 0, right? So now I can write this inside conductive flux as minus k del T, that is coming from the Fourier law. The heat flux is minus k into temperature gradient, and the temperature gradient is dou T by dou Z. at Z equal to L. This is very important, at Z equal to L. This is the conductive flux, and this is the flux that goes out in the convective form, and the convective form is given as something like this, where now H is the heat transfer coefficient, right, for this with the surrounding of the temperature difference, the temperature at the surface and the ambient temperature. Keep in mind that the temperature of the surface will not be same as the ambient. Let us say I keep an iron slab which is hot to begin with, and the ambient is, let us say, at room temperature. So just near the surface or at the surface, it is pretty hot, right? So there is going to be a temperature gradient from the surface to the bulk of the air in the room. The bulk of air has a temperature of Ta, but the surface itself has a temperature, whatever is defined there, let us say TL, right? That temperature will drop from TL to Ta in a small thickness in the air, right? And that is what is known as a thermal boundary layer, right? If you go near the hot iron slab, what you will see is when you are far from it, the temperature is close to the ambient. As you clearly start to approach it, very near to it, temperature will be somewhere in between its surface temperature and the ambient temperature, and when you touch it, the temperature is going to be the surface temperature, right? So there is going to be a small region or the region of influence near the slab, for which you will see the effect of the fact that the slab is hot, but far off from it the temperature is ambient, right? So let us say the bulk temperature is Ta and the surface temperature is, let us say, T defined at L, then T minus Ta becomes the temperature difference between surface and the bulk, right? And the heat transfer mechanism outside is convection, and that is characterized by the heat transfer coefficient H. Keep in mind that there is no temperature gradient as in the case of conduction, right here. For the convection, it is simply H into delta T. That is what is coming here. And keep in mind, I am talking about fluxes always, so it is already per unit area, per unit time. If I have to get the total heat added, I have to multiply this with the corresponding area. So at this boundary top surface, I need another boundary condition that is given by something like this. So now I have figured out two boundary conditions for this case in Z direction. At Z equal to L, we have this. At Z equal to 0, we have this. An initial condition we already know that T is equal to T naught everywhere inside the slab. In the beginning, we assume that it is uniformly heated. So now we have the set of the equations. This is my governing equation which I have to solve, and this requires three conditions. One initial condition, so I am defining temperature as something like this. T is a function of Z and T. So at T equal to 0, at small t equal to 0, T Z0 becomes the initial condition, and that is equal to some T naught, that is equal to some T naught. And at the Z equal to 0, that bottom, that is my center line, dou T by dou Z is equal to 0. And at the top surface, we have equality of the fluxes, and that gives me this function, that is conductive flux is equal to convective flux. So going forward, I want to solve this equation, and one of the methods of solving these kind of equations, if you have learnt about it, is known as the variable-separable method, right? It does not always work, but it does work in some cases. When it works, it gives you beautiful solutions, series solutions. So can I assume that this T temperature, which is a function of small z, small t, can be written as some function exclusively of g or only of g and some function only of t? And if I can do that, then I can essentially reduce this partial differential equation, as we will show, into some ordinary differential equations in terms of this zeta and this theta functions, right? And then of course, ordinary differential equations are easier to solve than partial differential equations, right? So, but the question is that can the temperature, that is generally a function of z and t, be written as a function only of z multiplied with a function only of t? If that is possible, then only we can proceed, right? It turns out that it is possible only if the boundary conditions that we have are homogeneous. What do we mean by homogeneous boundary condition? Is in this case the temperature variable and its gradient dou T by dou Z. Some linear combination of that should sum to 0, right? For example, either T would have been equal to 0, it will make it homogeneous. That is clearly not the case here. Or something like T plus dou T by dou Z is equal to 0, that is equal to 0, some linear combination, or T plus twice of this equal to 0, some linear combination of temperature and dou T by dou Z, or something like dou T by dou Z is equal to 0, that is the first one is already homogeneous, but second one is not. Why? Because apart from the temperature coming here, we also have an ambient temperature. If this minus Ta would not have been there, then I can say that only until the first term we have a linear combination of temperature and dou T by dou Z that is equal to 0. Essentially, we have something like Ht minus K dou T by dou Z is equal to 0 if Ta is equal to 0, right? But clearly Ta is not equal to 0, right? So, therefore, the variable separable will not apply for the equations in this particular form. However, we can do something here. So, what I can do now is I can redefine the temperature in a manner that will make my boundary conditions homogeneous. Can we do that? And turns out it is we can do that. This is my original set of equations which was giving me a non-homogeneous boundary condition. I want to make it homogeneous. What I do is I redefine the temperature, or I define a new variable that is not the temperature, but the temperature difference. So, I define something like a Td, that is T minus Ta. And then if I plug it in here, you see that Ta is anyway a constant term. So, my partial differential equation is pretty much unchanged. We simply replace T with Td. But then if I look at now the boundary conditions, initial condition will be something like T naught minus Ta now. T naught was a constant, Ta is still a constant. So, T naught minus Ta is also a constant. Mathematically, there is no difference, right, in terms of solution capability. But in the boundary condition, the first boundary condition is still 0, which is already homogeneous. But in the second boundary condition, earlier we had T minus Ta, but just because we have now redefined the variable, now we have H into Td. And on the left hand side, since Ta is constant, I still have Td. And now we have a homogeneous boundary condition, something like a linear combination of Td and its derivative is now is equal to 0. So, now we have a homogeneous boundary condition, and now we can apply the variable separable method. I will do one more thing just to make our solution neater, right, and make more physical sense, is I will define a dimensionless temperature. I already have figured out that T minus Ta is a variable change I should do, but now I will divide it by T naught minus Ta. This will give me a dimensionless quantity, and it is not going to affect my equation because this constant is going to be the same in the left hand side and right hand side. So, pretty much I will get the same partial differential equation in terms of this dimensionless temperature. But the advantage we have is now the equation looks much neater, right. For example, the initial condition now for T is equal to T naught, this T cap becomes equal to 1, right. And you can also see that what is going to happen at steady state, if I wait long enough, then the temperature of the slab should eventually become equal to the ambient temperature. So, when T is equal to Ta, T cap becomes 0, right. So, T cap goes to 0 for infinite time for sure. So, now we have a dimensionless temperature that is going from 1 to 0 regardless of what is the ambient temperature and the temperature of slab, and the same thing holds true if the slab was colder to begin with and the ambient was hotter, we always have a T cap variable, dimensionless temperature, that is always going from 1 to 0, always decreasing. That makes it much neater. The boundary condition 1 is unaffected because the denominator is still a constant, and boundary condition 2 is also more or less unaffected, right? We simply replace T by T cap, the denominator will cancel in both left and right. Now I also define a dimensionless length and time. For length, we have a easier choice. So we have the length of the half slab, that is this length. So if I define Z cap as Z by L, it is varying in the range of 0 to 1, just like temperature. Now Z cap is also varying between 0 to 1. And now I can plug it in Z cap in the equation, the L square will come out because we have a second derivative of Z. And then we have something like K by rho Cp L square. And since temperature is already dimensionless, Z is already dimensionless now. So now we only have a dimensional variable time. And therefore, whatever we have on the right hand side, it will have a unit of something like 1 over time, right? And that's what exactly is happening here. So I can define now a time scale, something like rho Cp L square by K, that comes from this. And if I do that, I can define a dimensionless time, T cap is T by tau. And if I do that, I will have now some kind of a PDE that is much simpler to look, bearing all the constants, because all the constants now are appearing in this time scale tau. And you will see this time scale indeed is quite useful for us. And now we have much neater initial condition, much neater boundary condition. And even in the last one, because we already had like h by k earlier, h by k coming from here earlier, and now from this fact that I have made z dimensionless, I can form a dimensionless number hl by k, that is also called the Biot number. And I will talk about more about the physical significance of this later, right? So I have simply reduced this slab heat transfer problem into a dimensionless problem, neatly looking, with all the variables which were there inside this time constant tau. Of course, the dependence on heat capacity, density, L and K all are there, but I can solve in the dimensionless form, just like we use Reynolds number in fluid mechanics. I now have a dimensionless temperature, a dimensionless time with respect to some time scale that contains all the variables in the problem. So this is my dimensionless form. So now Z cap is from 0 to 1. T cap varies in the range of 1 going to 0, right? And now we have a dimensionless group, the Biot number. Okay? And now I can apply this variable separable form. So I can write this T cap as a function of only Z. This is my zeta function, and as a function of only theta. If I plug it in this equation, I can now write from the left hand side becomes zeta into theta prime, where theta prime is d theta by dt. Keep in mind, I have replaced the partial derivative with now the proper derivative. Why is that? Because zeta is not a function of time, so zeta comes out, right? If I plug in t cap as zeta of z theta of t cap, then zeta will come out because zeta is not a function of t. That's what happened here. And the derivative of theta, now the theta is only a function of time, so there is no question of partial derivative. So theta prime is simply d theta by dt, right? Similarly, on the right hand side, the theta will come out because theta is not a function of z, right? So we have theta, and then second derivative of this zeta function, and second derivative of zeta is again simple derivative d2 zeta by dz square, not partial derivative. Again, keep in mind that it's already in the dimensionless notations, right? So I can rearrange this and I can get theta prime by theta is equal to zeta double prime by zeta, where the derivatives again with respect to whatever is the independent variable there. Theta prime is derivative with respect to time, and zeta double prime is derivative, second derivative with respect to z. Now, it is not very difficult to see that this has to be a negative number. Why? Because t cap is going from 1 to 0, right? So, therefore, the gradient of theta in time must be negative, right? And in order to ensure that it is negative, I am basically writing as some minus lambda square, where lambda is a real number. So, as long as lambda is real, lambda square is a positive quantity. So, minus lambda square will be a negative quantity. We will see why we have defined in this way. It just simplifies our math later, right? But the key lesson is that since we have made our dimensionless variable in a manner that t cap is going from 1 to 0, I can take that the theta prime, that is d theta by dt, must be less than 0 for the temperature to decrease with time, and therefore I have put a negative lambda square, right. So, now this equation gives me essentially two ordinary differential equations. One, considering the first and the third term, I get an equation in time only, right, and if I solve that, I get this kind of a general solution. Theta t is something like some constant multiplied with exponential of minus lambda square t. You can always convince yourself by taking its derivative and putting it there. So, derivative of this with respect to time is like something like C1 into minus lambda square exponential of minus lambda square t cap, and that gives me minus lambda square theta, right. On the other hand, if I equate the second and third term, that gives me another general solution in terms of cosine and sine. Again, you can take a second derivative of this. The first derivative gives me of cos minus sine, second derivative is minus cos. So, zeta double prime essentially will give me something like this. You can convince yourself by doing that. So, now I have this general solution for theta and zeta, and now I can plug in my initial and boundary conditions to basically get this constant values, right. Let me first use the boundary conditions. The first boundary condition is at z equal to 0, z cap equal to 0, and if I plug it in my definition here, again theta will come out because theta is not a function of z. So, we have essentially zeta prime at z equal to 0 is equal to 0, right, and the zeta prime I can do, this is my derivative, that is equal to 0. If I put z cap is equal to 0 here, the first term becomes 0 anyway, and the second term gives me 1 because cos 0 is equal to 1. So, I get C3 lambda is equal to 0. I do not want lambda equal to 0, because if lambda is equal to 0, then theta prime by theta is also equal to 0. That means there is no change with time. I do not want that, right. So, therefore, I do not set lambda equal to 0, I set C3 equal to 0, right. Now, I apply the second boundary condition. I already have figured out C3 equal to 0, right. From second boundary condition, I get minus zeta prime at z cap equal to 1 is bi at sigma at z cap equal to 1, right, and this gives me lambda sine lambda, because now this term, second term is already gone, only first term is remaining. I take a derivative and I get something like lambda sine lambda by putting in z cap equal to 1, that is equal to that bi cos lambda, right. On the left hand side I have done this, on the right hand side I have done this, right, and that gives me the equation that should give me the value of lambda. Lambda tan lambda is equal to my Biot number bi. Now, it turns out that this particular equation which I have got, that equation has to have many solutions. It's a trigonometric equation. I can plot this function lambda tan lambda minus bi is equal to 0 or lambda tan lambda is equal to Bi, right? And let us say I am showing you for Bi equal to 2, you can see it crosses the curve many times. That means that there are infinitely many solutions, or in other words, the solution has some kind of periodicity in that, right? So it is changing between every 0 to pi by 2 there is a solution, pi by 2 to pi there is a solution, then it is 0 to pi by 2 is solution, then again solution, then again solution, right? So every time it crosses the axis there is a solution, right? And more importantly, what we also see that my temperature is anyway a even function in lambda, because if I put lambda equal to minus lambda here, I will get the same solution. Cos of minus x is cos of x, and the first term is unaffected. So I will ignore the solutions for the negative value of lambda, and I keep in mind that there are many solutions of lambda. In fact, for every range from n pi to n plus half pi, let us say between 0 to pi by 2 we have a solution, then pi by 2 to pi we have a 0 to pi by 2 we have a solution, then pi to 3 pi by 2 we have a solution, and so on, right? And therefore we have the first solution something like lambda naught in the range of 0 to pi by 2, that is right here. Then we have lambda 1 between pi to 3 pi by 2, that is somewhere here, and so on, right? So now we have so many solutions. So what we can do with that? So now we can use what is known as the principle of superposition, because every lambda value we are getting from here, that constitutes a solution, and a linear combination of any solution is also a solution. That is what is given by the principle of superposition, and we can convince yourself by putting it in your partial differential equation. So in general, therefore, we write a series form from n equal to 0 to infinity. We ignored the negative n values because my function is even, and whatever we have we can include in this factor, a factor of 2 or whatever is important here, right? And then we have basically this series form because we have so many values of lambda, which is a solution to this, right? Now this series form can be pretty much unsolvable if every consecutive term is bigger than the previous term. But then if every consecutive term is lesser than the previous term, or we have a diverging series or we have a converging series, then we can hope to have a solution to this, right? Let us hope that it is a converging series. Now we are left with how will we figure out these constants a n. So now we are left also with the initial condition, right? And if I plug in the initial condition, that is t prime t cap is equal to 0, I get something like this, and then I can use the idea of orthogonality and things like that to figure out these constants a n. I am not going into how we can derive this, besides the point, right? But we have now a method in which we can analytically derive the expression of the dimensionless temperature as a function of dimensionless z and dimensionless time. It is not always possible, and we have to do certain simplifications or modifications in our math in order to make it happen, and it is only possible in some fortunate cases where we can do that, but in this case it is possible to do that. So with that I conclude here. In the next lecture I will begin with this particular point, and then I will discuss more about the physical meaning of the Biot number and what we can derive from the solution of this one-dimensional heat equation in a slab, and then how we can apply this knowledge in similar problems in the heat equation and other fields. So with that I want to conclude here. Thank you so much.